Sir, good morning, sir. My name is J. Charanteja. I am from CSC AML, third semester, second year. Today, my topic is about design of real-time task scheduling for embedded systems. Introduction to real-time task scheduling. Real-time task scheduling is critical for ensuring timely responses in embedded systems. It involves allocating process time to tasks based on their priority and timing constraints. Proper scheduling guarantees system reliability and performance in real-time applications. What is real-time scheduling? A real-time scheduling is a embedded system is a component of the RTOS or bare metal firmware that decides which tasks to run, when it runs, for how long it runs, when it permits other tasks. Unlike general purpose OS schedules, real-time schedulers guarantee deadlines. Embedded systems need deterministic timing for tasks such as sensor sampling, motor control, ADC conversations, communication protocols, satis safety functions. Timing failures can break a product or become dangerous. Example automotive, medical, and robotics, etc. Characteristics of embedded systems. Embedded systems are dedicated to specify functions within large devices or systems. They often require deterministic response to external events. Constraints include limited resources, power efficiency, and real-time performance needs. Hardware versus software real-time. Real-time systems are classified into hard real-time and soft real-time. Hard real-time. Missing a deadline, catastrophic. Examples airbag deployment, place marker plus control, anti-lock braking system like ABS. Soft real time, missing oscillation deadlines is not equals to failure. Example audio streaming, video playback, consumer IoT devices. Scheduler design depends heavily on which category you target. Types of real-time systems. Hard reality system requires absolute adherence to deadlines with no exceptions. Soft real-time system aim to meet deadlines most of the time. Tolerating oscillation misses. Firm real-time systems have deadlines that are important, but missing them does not cause catastrophic failures. Key parameters for real-time scheduling. Every periodic task has period, how often the task should run, worst case execution time WCET, maximum time needed to complete, deadline must finish by the time, phrase or offset when it should first run. Example task A T equals to 20 minutes, WCT equals to 5 milliseconds, D equals to 20 milliseconds. The scheduler must ensure CPU utilization stays below safe limits so that all tasks fit within their deadlines. Types of real-time scheduling. There are three major categories. A. Static scheduling, office scheduling. This schedule is computed ahead of time, used in hard real-time systems. Example: cycle executives, time target architect TTA. Characteristics of this real-time: simple, highly deterministic, no runtime overhead, no dynamic tasks allowed. Task model and scheduling parameters. Tasks are characterized by attributes like arrival time, execution time, deadlines, and priorities. Scheduling parameters include primitiveness, predictory, and resource sharing. Accurate modeling of tasks is essential for designing effective scheduling algorithms. Dynamic scheduling and static priorities. Tasks have fixed priorities, and the key algorithms are rate monotonic scheduling. Shorter period equals to higher priority. Primitive Gardentine schedule if type of period control loops. Dynamic schedulers with dynamic priorities. Priorities can change during runtime. Earliest deadline first, EDF. Tasks with nearest deadline gets highest priority. Higher CPU utilization, more complex, used in multimedia or robotics. Cyclic execution, a simple and robust scheduler, uses a main loop, and the design of this loop is divide time into major cycles, frame of 10 to 20 milliseconds. Inside it, place fixed sequence of tasks. Each task is executed once per frame. Common scheduling algorithms. Rate monotonic scheduling RMS assigns priority based on tasks periodicity. Earliest deadline first EDF dynamically prioritize tasks with the nearest deadlines. Fixed priority scheduling is simple but may not always yield optimal resource utilization. Pros and cons for this: external predictable, non-permission needed, very low CPU overheated. Cons for this: no dynamic tasks, hard to modify once deployed, best for very safety critical bare metal system. Design consideration for real-time schedulers: ensuring low overhead to minimize impact on task execution times, guaranteeing deadline adhere through appropriate algorithm selections, handling tasks synchronization, resource sharing, and priority inversion issues. Primitive real-time scheduling. Primitive allows a high priority task to interrupt a low priority one. How it works means each task has a priority. Scheduler runs on time interpret. If a higher priority task become ready, swap contexts. Needs for this are context switching, primitive kernel support, priority inheritance to prevent priority inversion. This is how real RTOS kernel operates. Free RTOS, ThreadX, Zerfree. Implementation of real-time schedulers. Use of real-time operation systems RTOS that provide scheduling frameworks. Incorporation of priority inheritance protocols to manage resource conflicts. Optimization of minimal context switching and interrupt handling delays. Performance evaluation and testing. Simulation and analysis are used to predict scheduler behavior under different loads. Metric includes task response time, deadline miss ratio, and CPU utilization. Testing in real hardware environments help verify system stability and real-time compilation. Challenges and further trends. Managing increasing complexity with heterogeneous and multiple core architectures. Developing adaptive scheduling algorithms for dynamic and unpredictable workloads. Integrating machine learning techniques for improving scheduling decisions. Conclusion. Effective design of real-time task schedulers is vital for reliable embedded system operation. Balancing responsiveness, resource utilization and complexity remains a core challenge. Ongoing research continue to enhance rescheduling techniques for emerging embedded applications. Thank you, sir. Thank you for listening me patiently. Thank you.